Hi everybody and welcome to Unit 2 Part 3 Notes. This is an exciting day of notes today because we're really going to be learning some things that we're going to use all throughout this whole year in chemistry. All right, so this notes is called Periodic Trends, and we're going to see how we can use the periodic table to figure out even more information about our different elements. All right, as we look at the periodic table, and you should be looking at your large periodic table, all right, one of the ones that I gave you, as we do this. The order of the elements, as you read from left to right, all right, is determined by the number of protons. Okay, or number of protons. We also know this as the atomic number. All right. This kind of odd shape of the periodic table, however, is actually determined by the electrons. All right, so it's actually determined by the electron configuration. So we learned about electron configuration in our last set of notes, all right? And what we will notice is that all of the elements, okay, in the first two columns on the periodic table, and I do want to stop and you want to add some definitions here, all right? When we talk about columns on the periodic table, those are called groups, all right? So groups are your columns, okay? I can never spell columns, right? All right, or your columns. As we go across the periodic table, the rows are called periods. Okay, so when I refer to group 1, I am talking about that group 2, and then so forth until we get to group 18 on our periodic table. All right, great. So as I mentioned, this odd kind of shape has everything to do with electron configuration. Everything in groups 1 and 2 are going to actually end, their electron configurations are going to end in S. Group 1 is going to end in S1, group 2, S2. So groups 1 and 2 are known as the S block. Groups 13 through 18, everything over here actually ends in P. Boron ends in P1, P2, P3, P4, P5, and P6. So groups 13 through 18 are known as the P block. This interior group here, all right, and that is groups 3 through 12. These are also known as the transition metals. All right, that is your D block group. So we have our S, our P, and then our D. Finally, all right, if we get down to the bottom of the periodic table here, you'll notice we have 14 across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That is our F block. And these actually get names. They're called the lanthanide and actinide series. All right, and that's our F blocks right here. So we have our S, our P, our D, and our F. If we forget, you can remember how many do each of these hold. Well, S holds 2, so there's 2 groups. P holds 6, so there's 6 groups. D holds 10, so there's 10 groups. And F holds 14, so there are 14 groups there. All right, fantastic. Now, as I mentioned before, okay, everything within the same group is going to have the same ending, all right? So, and this is because, so here we go, same group, same end of electron configuration. Okay, the end of your electron configuration is also known as your valence electron. So let's just remember, because this is going to be really important, our valence electrons are our highest energy. So you want to write this down. Highest energy electrons. Okay. They're going to end up being the ones, when we start making compounds and talking about bonds, they're going to end up being the ones that actually do that actually bond on to other atoms. So again, it's going to become really, really important. All right. Elements within the same group will demonstrate similar properties because they have the same number of valence. So for example, everything in group 1 ends with a configuration of S1 and has 1 valence electron. Okay, so nice and straightforward like that. All right, fantastic. So we're going to take this and we are going to move on to what are known as ions. And again, ions are going to become very, very important to us when it comes to making compounds and reactions and all of that good stuff. All right. Remember, when we use the word atom, it means that your number of protons equal your number of electrons. Okay. Ions, however, that's when you're going to end up gaining or losing electrons. So when atoms gain or lose electrons, they become ions. They are no longer neutral atoms. So we don't call them atoms anymore. We call them ions. Well, why do they want to gain or lose electrons? Well, the whole idea of chemical bonding, why they would want to gain electrons, lose electrons, is because they want to be more stable. And a stable element has a full outer energy level of electrons, a full valence. You know who already has a full valence? Okay, the noble gases. So to become more stable, they want to become happy. So we're going to use the word happy instead of stable, like the noble gases. So now let's talk about who are these noble gases. All right, bringing back my periodic table here. The noble gases live right here in group 18. All right, these are my noble gases. And these all have full outer shells. Helium ends in electron configuration is 1s2. The first energy level only holds 2 electrons. It's totally full. It's happy. The rest of these all will end. So this again ends in S2, but the rest of these all will end in P6. All right. So these all have a full energy level. So they'll end in S2P6. 2 and 6 is 8. 8's going to become an important number to us. All right. So again, if we did the electron configuration, let's say for neon, neon is going to be 1s2, great. 2s2, 2p6. 2. All right. So let's do that here. Neon, 1s2, 2s2, 2p6. All right, great. So if I were to ask you for how many valence electrons that is, you're going to look for the highest energy level, which is 2. You're going to underline anything that has a 2 in front of it. How many electrons is that total? 2 from the S, 6 from the P. That's going to give us the magic number 8 electrons. If you did that for any of the following, you would get the same. All right, because the highest energy level is always going to be a combination of that S and that P. So that's where we're getting this magic number 8 from. That magic number 8 leads us to what is known as the octet rule. To be stable, atoms want 8 electrons in their outer shell, with the exception of hydrogen and helium, because they're just in that first energy level, they're just going to want 2. To do this, atoms can lose or gain electrons. Remember, those outer shell electrons, and I know I'm being very repetitive, are known as your valence electrons. Really important. All right, some other terms I'd like you to add to your notes. When we're talking about ions, if we get a positive ion, this is a positive sign, we call it a cation, and that's how it's pronounced. It's cation, not cation. It's a cation. All right. If we have a negative ion, we call that an anion. All right, so you've got to remember those 2 terms. All right, so let's look at some examples and see why we have these different atoms turning into ions. All right, so let's take a look at sodium. First off, we're going to look at our periodic table, and we're going to see that sodium has 11 protons, all sodiums, and the atom of sodium has 11 electrons. Great. I'm going to go ahead and do my electron configuration for this. You might want to pause and do that for yourself as extra practice. It's 1s2, 2s2, 2p6, 3s1. All right, fantastic. So that's the electron configuration for sodium. If I were to ask you how many valence electrons does sodium have, highest energy level is 3, so there's just 1 valence electron there. All right, well, what is sodium going to do? It wants to have a full outer energy level. All right, so remember, what does it want? It wants a full outer energy level, which is that magic number 8. Is sodium going to lose this 1 electron or try and gain 7? Which do you think is easier to do? Absolutely, it's going to lose that electron. So when it loses that electron, that's going to go. This is going to become sodium's electron configuration. But now I am no longer sodium atom, I am a sodium ion. I still have 11 protons. That will never change as long as I'm sodium. But now I've lost an electron, and now I have 10 electrons. I have 1 more positive than I do negative. So sodium now becomes the positive ion. All right. Okay, fantastic. Let's try the same thing for chlorine. Chlorine has 17 protons, and therefore an atom has 17 electrons. Let's go on ahead, pause, do the electron configuration for chlorine. All right, fantastic. There's our electron configuration for chlorine, looking for the highest energy level represented, which is our 3rd energy level. So how many valence electrons does chlorine have? It has 7 valence. All right, do you think chlorine is going to want to gain an electron from someone or give 7 away? All right, it's going to want to gain an electron. So we're going to add an electron to that. So now my new chlorine still has 17 protons, but the electrons are now 18. All right, so now my chlorine has a -1 charge. That is an ion of chlorine. Now, you may be saying, oh, well, what's the difference? It's just a little charge sign. And I want to give you an example of how incredibly important the difference is between the ion, all right, and just the atom, okay? All right. So an ion of sodium, that's what's in table salt. We actually need sodium to survive. It's super important to us. Same thing with an ion of chloride. All right, both of these are incredibly important and actually vital for life and something that we eat every single day. All right. In contrast, sodium, atomic sodium, just regular Na without the charge, that actually explodes if you put it into water. All right, so if you eat sodium atom, most likely it will kill you. If you eat a sodium ion, I guarantee you've probably already done that today and you're fine. All that's different is the fact that it has lost an electron. Okay, so chloride, same thing. Chloride ions, fine, we eat them all of the time. Chlorine, you should be used to hearing about chlorine because where do we put chlorine all of the time? We put it in swimming pools. Why do we put it there? To kill things, because it's a poison. All right, so the difference between having the charge and not having the charge is really, really important. Now, you don't need to do all of this work just to figure out what's going on with these elements. You can just look at the ion. So here we go. I have calcium 2+. Well, I'm going to look at my periodic table. All calciums must, in order to be calcium, have 20 protons. I have the charge already. It's 2+, so that means it has 2 more positives. You can't change these protons. The electrons, however, will change. How many electrons are you going to have? You're going to have 18 electrons. All right. I'd like you to do the same thing there for the nitrogen ion. All right, all nitrogens, in order to be called any type of nitrogen, must have 7 protons. Okay, and as far as their electrons go, this is a nitrogen ion. I have a 3 negative, so that means I need 3 more negatives than positives. So 3 more than 7, I have 10 electrons right there. All right, fantastic. Now, we can use the periodic table to help us so we don't have to work quite as hard as we've been working. And this falls under what is known as oxidation numbers. Oxidation numbers is the most common charge, so it's just another word for charge, that an element has after it has lost or gained electrons. All right, oxidation numbers follow periodic properties, which means that for many groups on the periodic table, every element within the group will have the same number of the same oxidation number. All right, so this is something really, really important, huge amount of stars. You want to absolutely memorize this. I'd even write this on top of your periodic table. Everything in group 1 has a positive 1 charge. Everything in group 2 has a positive 2 charge. Aluminum will always be positive 3. Zinc will always be positive 2. Silver will always be positive 1. Moving over to group 17, which is where chlorine lived, chlorine was negative 1. Chlorine and everything else in that group will be negative 1. Group 16, everything is negative 2. And in group 15, it's really just nitrogen and phosphorus will always be negative 3. Again, these are super important. Expect you to know these. We're going to be using them all of the time. Let's look at a little bit of practice. All right. And let's see how we can use this. All right. Again, using your periodic tables and your notes. Identify the following element by name, symbol, and whether it's a metal versus a non-metal. So let's take a look at our periodic tables. And I just want you to jot this down, whether it's in your notes or on your periodic table. Everybody sees on this version of your periodic table, you have a stair step. I wrote that stair step in on purpose. Everything to the left of the stair step is considered a metal. All right, so that's left of stairs. Everything to the right of that stair step is considered a non-metal. Okay, so that's right of stairs. We're going to be using this a huge amount, particularly in our next unit when we start talking about writing formulas for compounds. So left of the stair step are metals, right are non-metals. All right, so let's take a look. Still using your periodic table, so have that out. So I have 3 protons. Okay, so who am I? I go to my periodic table. All right, and I know this one's a little tough to read, but anything with 3 protons is lithium. Okay. I want you to write the name for lithium, okay? I'm just gonna go ahead and write the symbol to save on time. So name, symbol, we're gonna take care of that. Is it a metal or a non-metal? Well, lithium here is on the left side of that stair step, so lithium is considered a metal. Okay, and is this an atom or is this an ion? Well, my protons and electrons are the same, so that's an atom, which just means I write lithium exactly like this with no charge. All right, so let's check out our next one. 16 protons. So if I'm 16 protons, check on your periodic table. I am sulfur. All right, great. Okay, well, sulfur is on the right side of the stair step, so I am a non-metal. But look, I have a different number of protons and electrons. So that must mean I am an ion. I have 2 more electrons. Remember, electrons are negative, protons are positive. I have 2 more negatives than positives. So I am an ion with a negative 2 charge. You can write the charge either before the 2 or after the 2. Typically, you're supposed to write it after the 2, but it's totally fine either way. All right, so take a second, find the element that is 50 protons. All right, so on our periodic table, we are looking for 50. Okay, and 50 is right here. 50 is tin, so that is tin. Okay, and am I a metal or a non-metal? Tin is to the left of that stair step, so I am a metal. And I'm going to write the symbol here. I have 50 protons and 46 electrons, so I'm not an atom. I am an ion. What is my charge? Well, I have 4 more positives than I do negatives, because remember, these are negatives, these are positives. So my charge is going to be 4+. Okay, great. All righty. So let's go through our next set of practice. Feel free to pause now if you'd like to try this practice on your own, or you can go ahead and do it along with me. How many protons, neutrons, and electrons do the following elements have? Okay, great. So right here I have Ag, which is silver, dash 107. Now, silver does not have a charge written on it, therefore it is an atom. Okay, so your number of protons are going to equal your number of electrons for this. And where am I going to find that? I'm going to look on my periodic table and I'm going to find silver, and silver has an atomic number of 47. All right, so that is how I know how many protons I have. To find my neutrons, 107, remember, is the mass number. So I'm going to go 107 minus 47, and that gives me 60 neutrons. So to write that nicely for your teacher, protons equal 47, electrons equal 47, and your neutrons equal 60. All right, let's go on here to strontium 2+. Now you notice here I have the 2+, so this is an ion. So in this case, your protons and your electrons will not match, but we can figure out what they are. So I'm going to find strontium on my periodic table. Strontium has an atomic number of 38, so it has 38 protons. All right, it has 2+ as the charge, so that means its negative has to be 2 less than it's positive, because we never change the positive, right? We never change those protons. So that means I have 36 electrons. I'm telling you the mass number is 88. So I'm going to go 88 minus 38, and that gives me 50, and that's my number of neutrons. So I'll write that over here. Neutrons equal 50. Okay, so there's my answer for that. All right, definitely pause if you have not before and give a try for our phosphorus example. All right, for phosphorus, the atomic number is 15, so I have 15 protons. The charge is 3 minus, so that means I have 3 more negatives than my positives. So that means that my electrons are going to be 18. Okay, again, I'm going to use that mass number and my protons, 31 minus 15, to give us our number of neutrons. So our neutrons equal 16. All right, great. Okay, next up. Hi, everybody. We're going to finish up the notes on periodic trends today, just with 2 more properties that do follow the trends of the periodic table. There's actually a lot of different periodic properties out there. And if you guys go on to take AP chemistry, you'll definitely dive very far into this and spend a lot of time. But we're just going to kind of go quickly through these. So another one is what's known as atomic radii. That's just the size of the atom. All right. And as we would imagine, and here's my little graphic here, as we would imagine, as we move from the top to the bottom, atoms get bigger. It makes sense. There's more energy levels. All right. Therefore, the atom is going to get larger. So the trend is that it increases, all right, from top to bottom. So as I go from the top to the bottom, I get bigger. You might also notice, though, you start kind of large over here on the left, and it gets a little smaller as you go over to the right. I'm not as interested in you guys worrying too much about why that happens, but the general trend is that it decreases from left to right. We're not going to focus too much on that. One we are going to spend a little bit more time talking about is what's known as ionization energy. All right. First ionization energy, and yes, there is a second and a third ionization energy. That's why it's called that. But we're going to just focus on first, is the amount of energy needed to pull the highest energy level electron off of an atom. All right. So what do I mean by that? Well, all of the atoms, as we know, have electrons. They have those high energy or the highest energy electrons. How much energy is it going to take to rip one of those off? Well, as you would imagine, noble gases are happy. They do not want to be messed with, so they're going to have the highest first ionization energy. Whereas group 1 elements, remember, they're like sodium, just have that 1 valence electron. They're almost more than happy to have that taken off. So as we look at the trend, all right, in general, if you look, here are first ionization energies. All right, look, all the top ones are noble gases, and all of the bottom ones, hydrogen, lithium, sodium, are our group 1 elements. Okay, so what do I want you to take from this? Group 1, very easy to take off that electron. Group 18, very difficult. Okay, so the first ionization energy, because the higher the energy, that's the harder it is to pull off, increases as you go from left to right across the periodic table. All right, so as we look at our periodic tables again, group 1, really easy to take off that, that electron. Over here, noble gas is really hard to take off the electron. And even our fluorine, chlorine, bromine, they don't want to take an electron off. They want to gain one, right? Like we did with our ions. So they're certainly going to have high first ionization energy as well. All right. It also increases from the bottom to the top. Okay. So the hardest one to take off, we would imagine, would be helium. All right, so if I'm comparing just helium, neon, argon, and so forth, helium would have the highest first ionization energy, then neon, and so forth. The reason behind that is that these outer electrons are very close to the nucleus, and the nucleus holds on to them. All right, so how do these impact reactivity? That's the next thing on your notes. All right, well, here we go. I'd like you to write this statement down. What this tells us, what this ionization energy tells us, is that atoms at the far ends of the periodic table, groups 1 and groups 17, tend to be the most reactive. Now, why is that? Well, group 1 is very happy to give off that electron. It just has one dangling out there, and if it loses that one, it can be just like a noble gas. Group 17 is very happy to take that electron in because it has 7 valence and it's ready to grab that one. If I were to ask you for the least reactive group of elements on the periodic table, they would be the noble gases. They already have a full outer shell. They're happy and good to go. All right, so this has been a long session of notes, but I do have one more little piece of information I would like you guys to jot down. Some of our groups go by more than just their numbers. They actually have names, and you are responsible for knowing these 4 names. Group 1 is known as the alkali metals. Group 2, the alkaline earth metals. Group 17 are the halogens, and then of course Group 18, as we've been referring to them, are the noble gases. All right, have a great day, everybody.